Okay, we have just 1 minute left, and I believe we can begin. So our today's speaker is Konstantin Druzhkov. You see the title, Internal Lagrangians and Gauge Systems. Kostya, you're welcome to start.
Oh, yeah, thank you. Thank you. First of all, thank you for the opportunity to discuss my results here. And let us begin with classical Hamiltonian formalism with canonical equations that arise in classical mechanics, mechanics of particles. So equations 1 are Hamiltonian equations for Hamiltonian H. Here we have some configuration manifold of the corresponding mechanical system. Local coordinates on this configuration manifold are Q1, etc., Qn. And we can consider infinite prolongation of system 1, that is system 1 with all its differential consequences. But we can consider system as a manifold with local coordinates, and this infinite prolongation changed nothing in the sense that our system still is a manifold with coordinates t, q1, etc., qn, p1, etc., pn, because all the derivatives can be eliminated using the infinite prolongation of system 1. And we obtain just some manifold with coordinates t, q1, etc., qn, p1, etc., pn. This is our system from geometrical point of view. But of course, a system of differential equations is not just a manifold. And here we have some additional structure. Here we have this total derivative with respect to t. One can see that this total derivative has form 2. It's a sum of partial derivative with respect to t plus something else, plus something that looks like Hamiltonian vector field. Sorry. And we can consider this system from variational point of view. It's very well known that Hamiltonian systems arise from Hamiltonian variational principle. But first of all, let's consider this system intrinsically, from the intrinsic point of view. We can say that our system is a bundle, right? Is a bundle P epsilon. Here we have cotangent bundle of the configuration manifold multiplied by real line as a total space, and the corresponding bundle is just projection onto the second factor, right? The corresponding variational principle is given by Poincare-Cartan form L. But what is important is that this form can be considered as a differential form on our equation manifold, on the total space of this bundle, right? So this form belongs to the intrinsic geometry of the original equation. We can consider paths through instantaneous states, that is just sections of this bundle by epsilon. They, from physical point of view, they play role of paths through instantaneous states. It's very well known that cotangent bundle to the configuration manifold encodes instantaneous states. It's called phase space also, right? And here we have just nothing but paths through instantaneous states. Sigmas are paths through instantaneous states, and they can be described intrinsically from intrinsic point of view. The corresponding variational principle is given by the formula 3. It's just the corresponding Hamiltonian action. We can use this Poincare-Cartan form. We can consider pullbacks along sections of this bundle, and we can calculate the corresponding integral. This is our action. So the main point of this slide is that we can consider Hamiltonian formalism is just from intrinsic point of view. It's just the Lagrangian formalism rewritten in terms of the intrinsic geometry of equations of motion. Besides, it was mentioned that our total derivative, our dynamics of our system reduces to Hamiltonian dynamics, that is dynamics given by Hamiltonian vector field, if and only if our system is autonomous and we are ready to use the trivial connection of this bundle. So we have additional structure here, actually. We should divide this vector field, this total derivative with respect to t, into two parts. We should cut off this, the first term, in order to obtain the corresponding Hamiltonian vector field. And we can do that using the trivial connection. Without trivial connection, we cannot do that. So without trivial connection, we cannot discuss Hamiltonian dynamics. We can discuss Hamiltonian vector fields that correspond to energy conservation law and so on, but it's not Hamiltonian dynamics. And that is why the whole story is not about Poisson structures and so on. In this sense, it's not about Hamiltonian vector fields. In most general case, Hamiltonian formalism is not about Hamiltonian dynamics. It's about the total derivative, of course, but not about Hamiltonian dynamics in the most general case. And we want to consider the most general case because we want to generalize it for partial differential equations. We are going to build the same story. We are going to consider the same construction for partial differential equations to introduce it. Yes, and also let me note that if we don't want to use Lagrangian transformation, then nothing really changes. Lagrangian transformation plays no geometrical role. It can simplify everything in coordinates, and this is the very role of Lagrangian transformation. But it can change nothing from geometric point of view. It's not required. Geometrically, it just doesn't require it. If we do not want to consider Lagrangian transformation, then we have just Lagrangian of our system. Our equation manifold becomes a product of tangent bundle to the configuration manifold multiplied by our real line, right? And Lagrangian plus equation manifold also gives us Poincare-Cartan form written in terms of, say, tangent bundle, right? So in this sense, Lagrangian transformation is not required at all. It plays no role, so we are not going to use Lagrangian transformation. Yeah, let me emphasize that the role of Lagrangian transformation is quite interesting because it simplifies everything in local coordinates. It allows one to understand how everything works, how we can describe degrees of freedom and so on. But from geometrical point of view, it plays no role. So the main question is, how can one describe the Lagrangian formalism in terms of the intrinsic geometry of differential equations? And the main idea is that the Hamiltonian formalism is a non-covariant version of the Lagrangian formalism written in terms of the intrinsic geometry of variational equations. So we are going to use Hamiltonian formalism. Here our plan of this talk. Well, first of all, if we have some system of differential equations and our system is embedded to some jet space, and we have some Lagrangian such that its variational derivative vanishes on equation manifold, then this Lagrangian produces a unique element of a certain cohomology group of our equation. And I'll refer to elements of this cohomology group as internal Lagrangians. Internal Lagrangians can be varied in a non-covariant manner within classes of P through properly defined instantaneous states. So we need some concept of instantaneous states for partial differential equations also. And instantaneous states are encoded by the lifts of involutive hyperplane distributions from the base of a differential equation. Here we consider differential equation as a bundle again. And in some cases, it's reasonable to consider such lifts gauge equations. That is why the word gauge arises in the title. Yeah, but there is an alternative approach to the description of Lagrangian formalism in terms of the intrinsic geometry, an alternative approach due to Maxim Grigoriev. This approach is based on the notion of intrinsic Lagrangian. It's a very nice approach, to be honest, but the only difference between this approach and the construction I'm going to discuss is that our construction describes Lagrangian formalism that originally arise on jets. We have some action on some jets, and we are going to encode this action in terms of the intrinsic geometry. While intrinsic Lagrangians, due to Maxim Grigoriev, describe Lagrangian formalism in other sense. They just should be considered parts of our original objects. So if our original objects are differential equations equipped with intrinsic Lagrangians, then this is also a description of Lagrangian formalism. So the only difference is that we are going to discuss Lagrangian formalism that originates on jets. It comes from jets. from action functionals on jets. So to describe everything, I have to introduce notation. Let pi be a locally trivial smooth vector bundle over n-dimensional base M, and rank of this vector bundle is m-dimensional fibers, denoted by x1, etc., xn coordinates in some coordinate neighborhood on M, and we consider a coordinate neighborhood U such that our bundle becomes trivial over it. And denoted by U1, etc., Um coordinates along the fibers of pi over U. These U1, etc., Um play a role of dependent variables. In local coordinates, the infinite jets of a section of the bundle pi at a point x0 in U is given by partial derivatives of its components. We have section, we have local coordinates, then we have its components. We can consider partial derivatives of its components. So accordingly, coordinates on our infinite jets, J infinity denotes the whole set of infinite jets of the bundle pi. So local coordinates on these infinite jets are given by the following function. The functions for here we have infinite jet of some section at a point x0, and coordinate xi is just coordinate of this point x0. Besides, we have some additional coordinates ui alpha. Alpha is a multi-index, and these coordinates are given by partial derivatives, corresponding partial derivatives. Alpha is multi-index. It's convenient to treat alpha as a formal sum, like alpha 1, x1 plus alpha 2, x2, etc. But still, these coordinates are just adapted coordinates, are given by partial derivatives. The main structure on jets is the Cartan distribution. The Cartan distribution is spanned by the total derivatives. Total derivatives, they are written under the formula 5. Yeah, and the Cartan distribution can be considered a connection on the bundle pi infinity, where pi infinity is a natural projection. Each infinite jet of a section at some point remembers its point, the corresponding point. So we have projection from infinite jets to the base space, the original base, and the Cartan distribution becomes horizontal distribution or connection on this bundle, on the corresponding bundle, pi infinity. Yeah, there is a dual description for the Cartan distribution. Namely, there is the ideal of Cartan forms, that is, differential forms that annihilate the Cartan distribution. That is just this ideal is generated by differential forms that vanish on the Cartan planes, on the planes of Cartan distribution. And local coordinates, a Cartan differential one form, Cartan differential one form, or contact differential one form has the form H, is just finite combination of basis forms, basis contact forms, and basis contact forms have this form. So they are just vanish on solutions because they vanish on Cartan planes. And we denote smooth functions on jets as f of p, f of pi. Yes, let eta be a locally trivial smooth vector bundle over M, and let f be a section of the corresponding pullback. The infinite prolongation of this set, or of this equation, is given by the following infinite system of equations, system 9. Epsilon denotes the infinite prolongation of our original system of equations. Here we have just all differential consequences of the original equation. So the infinite prolongation contains all differential consequences of the original equation. And since this system is given by differential consequences, we can restrict Cartan distribution from jets to the equation manifold, to the infinitely prolonged system of equations. And if we consider this system not just manifold, but a bundle, then we also have connection on this bundle. This bundle is just restriction of pi infinity to the equation manifold. So Cartan distribution becomes a connection on our equation bundle. We can treat equations in two ways, as manifolds and as bundles, and it's convenient to consider equations as bundles, at least in this context, in the context of my talk. It's not necessary though, but it's convenient. Well, let's discuss internal Lagrangians, these elements of certain homologies that encode Lagrangian formalism. If L is an element of this module of horizontal n forms, that is just n forms on the base space pulled back to our infinite jets, and with coefficients in smooth functions. We call such elements, such forms, horizontal n forms, and if L is a horizontal n form, such that its variational derivative vanishes on the equation manifold, then there is a Cartesian form that satisfies the relation 11. So here we have the Durand differential of our horizontal n form plus Cartesian form minus the corresponding variational derivative. This expression is just Euler operator of the Lagrangian or variational derivative. So E of L and this expression are the same. This is the definition of Euler operator in coordinates. According to not identity or to some other constructions, there is a Cartesian form such that the difference between the Durand differential and the variational derivative belongs to the set of twice Cartesian forms. That is, twice Cartesian forms arising in the following construction. We can consider our ideal of Cartesian forms. We can consider its square, and elements of this square are just twice Cartesian forms. So elements of this square are like twice degenerating solutions. In simple words, elements of the square are just twice degenerating solutions, while Cartesian forms at least once degenerating solution. They vanish on solutions or on Cartesian planes. And twice Cartesian forms square degenerate, twice degenerate. Yeah, we need these forms L plus omega L because their restrictions to epsilon, to the infinitely prolonged manifold, play the role of Poincaré Cartan forms. So they encode our Lagrangian formalism, or Hamiltonian formalism, if you want. All such restrictions, this form omega L is not uniquely defined here. That's why we have to consider all such restrictions. And all such restrictions lead to the same element of this group, this factor space. So here we have n forms on epsilon, such that their Durand differential is twice Cartan form. It's easy to see that according to this membership, the Durand differential of this form restricted to epsilon is just twice Cartan form because the restriction of this term is trivial, right? So we have an element of this set, of this space, differential on forms such that their Durand differential is twice Cartan form, and we consider them modular elements of the sum, modular twice Cartan forms plus Durand differentials of Cartan forms. The point is that all such restrictions determine the same element of this quotient. And the cohomology class, horizontal cohomology class of the original Lagrangian produces a unique internal Lagrangian that is element of this factor. The only difference between this quotient space and this quotient space is that here we have not C lambda, but just lambda. We consider arbitrary exact forms here because we discuss cohomology classes of Lagrangians, not the Lagrangians themselves. So by internal Lagrangian, I mean an element of the group of vector space 13, and internal Lagrangians include cohomology classes of Lagrangians. Yes, let's discuss how we can obtain, how we can derive the corresponding forms omega L. For a section of this pullback, for a section phi, for section phi, we denote by E phi the corresponding evolutionary vector field. This evolutionary vector field is given by formula 14. And we can use the knot identity to derive such forms omega L. The knot identity states that there is Cartan and form such that the interior product of the corresponding evolutionary field and omega L is just horizontal and minus one form. Horizontal and minus one forms are defined in the same manner. Such that this membership holds, and the formula 15, the equality 15 also holds. Here we have, on the left-hand side, we have just Lie derivative of our Lagrangian with respect to arbitrary evolutionary field. And on the right-hand side, we have the interior product of this evolutionary vector field, the same evolutionary vector field, with our variational derivative of the Lagrangian, plus horizontal differential of this interior product. Horizontal differential is just the run differential in terms of total derivatives, where we change partial derivatives to total derivatives, with total derivatives. Internal Lagrangians can be considered cohomology classes of quotient complex. We can take the round complex, just complex of differential forms, and consider its quotient by twice Cartan forms. And we can calculate the corresponding cohomology, and internal Lagrangians are elements of some group, of some cohomology group. The filtration that is presented here, filtration of the Durand complex, lambda of epsilon, with twice Cartan form, then thrice Cartan form, and so on, leads to the spectral sequence for the Lagrangian formalism. So internal Lagrangians arise with the corresponding spectral sequence as elements of some group of the corresponding spectral sequence. And it was to mention that there is the Vinogradov C-spectral sequence that is produced by similar filtration, but here we have all terms. We have the round complex, Cartan forms complex, Cartan complex, twice Cartan complex, etc. While in the case of the Lagrangian formalism, there is no Cartan complex here. Our filtration starts with twice Cartan complex. So this is the only difference between the corresponding filtrations. And if we have some embedding of our equation to some infinite jet manifold, then each internal Lagrangian of epsilon can be extended to the jet manifold. That is, each internal Lagrangian is produced by some Lagrangian on the corresponding jet manifold. This extension operation is ambiguous, but the corresponding extension is global, at least. But the point is that the main point of this talk is that this extension is not required at all. Everything can be formulated intrinsically. Besides, internal Lagrangians lead to the corresponding intrinsic version of the Noether theorem. Yes, let's discuss how instantaneous states are encoded by the lifts of involutive hyperplane distributions. So, by a spatial distribution on epsilon, we mean the lift of an involutive regular distribution of rank n-1 from the base space M, n-dimensional base space M. So we have some involutive hyperplane distribution. We can consider its lift because we have Cartan connection. Cartan distribution can be considered a connection on our equation 1. And we can lift any distribution from the base space to epsilon. And if we have some involutive hyperplane distribution on the base space, then we can lift it to epsilon. Sorry. And a typical example is when M is just real vector space and dimensional real vector space with coordinates x0, x1, etc., xn-1, and the coordinate x0 plays a role of time. We can consider as small a distribution on the base. This distribution is spanned by partial derivatives with respect to x1, etc., xn-1. Besides, we have some Cartan distribution on our equation manifold, and this Cartan distribution can be described in terms of lifts of the corresponding partial derivatives. These total derivatives operators denote lifts of the corresponding partial derivatives. Since it's a connection, we can lift everything. So they are lifts of the corresponding partial derivatives. And then the corresponding spatial distribution on epsilon is given by lifts of spatial derivatives. That is dx1, etc., dxn minus 1. Of course, we have this model of Cartan-1 forms on our equation. This model is generated by restrictions of basis contact forms to the equation manifold. And similarly, we can describe a model of differential one forms that annihilate our spatial distribution. And this model is generated by the restrictions of basis forms to the equation manifold and the form dt in this case, in this example. So from physical point of view, this S small, lowercase letter s, defines the word simultaneous. This is almost the same thing as the reference system in physics, but here we have no time. We have only space in this sense, and something like time coordinate can be introduced arbitrarily. So we have no time error, no time concept, and so on. But we have leaves of the corresponding distribution, and these leaves can be considered as sets of simultaneous events. So we have the word simultaneous. From physical point of view, we have the word simultaneous while we have no time. Quite specific situation in this case. And maybe I should mention right now that there will be no time concept at all during our talk. So Hamiltonian formalism is not that. Oh, okay, we'll discuss it later in more details. Besides, of course, we have the corresponding filtration of the Cartan complex with these with complexes of differential forms that annihilate our spatial distribution. There is the corresponding ideal of such forms. We can consider square of this ideal. This square gives us a complex of the corresponding forms, and so on. We obtain the corresponding filtration 20. And since each plane of the spatial distribution is just subspace of the respective Cartan plane, we obtain dual inclusion, and this dual inclusion gives rise to morphisms of the spectral sequences. I'll discuss it in more details later, but it's just to mention. I decided to mention it here. So let's discuss pass through instantaneous states. Integral manifolds of spatial distributions are local solutions to the respective spatial equations. At least we consider them local solutions to the respective spatial equations, and they represent local instantaneous states. Here I use the word represent instead of the word are. Like, not they are instantaneous states, but they represent instantaneous states. I have to do that because in some cases, spatial equations should be considered gauge equations. And then instantaneous states are given by equivalence classes of solutions and not just by solutions themselves. So, generally speaking, solutions to a spatial equation represent instantaneous states. So let's define S sections. A section of the bundle by epsilon is an S section, where S is a spatial distribution in epsilon on its total space. A section sigma is an S section if the formula 21 holds for any point of the base. So here we have something like a condition of something that reminds the condition of covariant constant section, of section to be covariant constant. We have the requirement that the differential of our section sigma at a point x sends the corresponding point on the base to the spatial sends the corresponding plane on the base to the spatial plane, the corresponding plane of spatial distribution. S sections encode pass through instantaneous states, but we are going to perturb them. So we need something like definition of paths in S sections. because if we deal with variational approach, variational formalism, then we should have not only such Pez sigmas, but we should. Sorry. Yes.
I'm
yes,
sorry.
yes.
In the first definition on this page, you apply the RAM differential to
No,
a
not
section.
not RAM. Just usual differential, that mapping of tangent spaces.
What do you mean by usual?
This is not the RAM differential. This is just differential that sends tangent space to tangent space. This linearization of our sigma.
Okay. Okay.
This is not the RAM differential yet. Sigma is a section, and it's just differential is a mapping. We have mapping, and we have this differential. Yes, and in order to perturb such sections as sections, we need the notion of Pez in as sections, and this definition proposes something like this notion, and it's quite natural. We say that a mapping of this form is a Pez in as sections if all such mappings are as sections. So gamma of tau is just gamma, and we have some point tau x. Say we have some point tau x, we can substitute tau and do not substitute s. The corresponding mapping becomes gamma of tau. So it's just gamma of tau is just the same gamma, but we have substituted the first argument here, fixed first argument. Then we obtain Pez through instantaneous, through S sections. And actually it's a Pez in S sections if all such sections of our equation bundle are S sections for all real numbers tau. So let's discuss non-covariant variational principle. That is, let's discuss how internal Lagrangians can be varied in a non-covariant manner within classes of Pez through properly defined instantaneous states. So if we have an internal Lagrangian and its representative, let me recall that internal Lagrangians are equivalence classes. Suppose that we have also some representative of the corresponding equivalence class. Then we can define variation, we can introduce the corresponding variational principle. So definition, an S section sigma is an S stationary point of the corresponding internal Lagrangian if for any compact oriented n-dimensional submanifold, the relation 23 holds for each Pez in S sections such that gamma of 0 equals to sigma and all points of the boundary Dn are fixed. So this is a compact oriented submanifold and dimensional. Maybe this submanifold also has non-trivial boundary. And if so, we require that the boundary points should remain fixed. We consider the corresponding Pez through instantaneous states through S sections, Pez in S sections. And we require that the perturbation of the corresponding integral must vanish in its first order, with respect to tau, for any such Pez. So just pretty standard definition of something like variational principle. But we do not use here concepts of some functionals and Banach spaces and so on. We can avoid all this stuff. So let us stress that the choice of a representative L has no impact here, and all solutions of epsilon are as stationary points of any internal Lagrangian. So solutions are always as stationary points for any internal Lagrangian, any spatial distribution, and so on. And besides, let us stress also that here in this construction we have no time. No time is involved. Time is not involved in this construction at all. Only spatial distribution we consider, right? So is time actually important for the Hamiltonian formalism? Apparently the answer is no, but maybe from some other points of view, it's not the case and so on. But at least according to this construction, time is not important for the Hamiltonian formalism. This construction just encodes Hamiltonian formalism in terms of the intrinsic geometry. So let's have a look at some example. Consider the Laplace equation, that is equation 24. We can choose x, y, u, ux, uy, etc. as local coordinates on the corresponding equation manifold. So we have here local coordinates. As local coordinates, we choose coordinates as local coordinates on the equation. We choose coordinates on the jet space such that there are no two derivatives with respect to y here. Just one derivative with respect to y is allowed. Because second derivative with respect to y is eliminated using this equation, and all derivatives that contain two indexes y are just eliminated due to the corresponding infinite prolongation. Let's consider the internal Lagrangian represented by the form L, differential form, that is the restriction of the differential form 26 to the equation manifold. It's easy to see that the first summand here is just Lagrangian of the Laplace equation, while second and third summand, second and third terms constitute the corresponding form omega L. So here we have nothing but integration by parts. We use just Noether identity, and maybe I forgot to say that the Noether identity is nothing but integration by parts. We consider left-hand side, that is the derivative, and just use integration by parts and obtain the corresponding form omega L. Of course, this form omega L is defined ambiguously, but we can use the corresponding equivalence class, at least. Well, now suppose that our spatial distribution or spatial equation, I'm going to use the word, I'm going to refer to them as spatial equations also. So suppose that our spatial equation is the lift of this distribution, of the distribution lowercase letter s, that is just the kernel of the covector field dy. Then our spatial equation is spanned by total derivative with respect to x. This total derivative has this form, the form 27. And the solutions to this spatial equation are given by real numbers and arbitrary and pairs of arbitrary functions of x. The formula 28 establishes the relation between pairs of functions and real numbers and the corresponding solutions to our spatial equation, our spatial distribution. It's easy to see that here we have these functions a of x and b of x, and this real number y0. And since we consider spatial distribution, then we can apply the corresponding total derivative with respect to x to all such relations and obtain its infinite prolongation. So if we apply the total derivative with respect to x to this relation, then we obtain the relation like ux equals to derivative of a, right? X derivative of a. And if we apply the same vector field to this relation, uy equals to b of x, then we obtain the corresponding component of our solution in terms of uxy, component uxy, and so on. So solutions to the spatial equation are encoded by real numbers. They can be considered as time moments, instants. And besides, we have pairs of functions. And each solution to the spatial equation is given by pairs of functions and vice versa. So any S section has the form 29. The only difference between S sections and solutions is that here we do not freeze this coordinate y. We do not fix the coordinate y. So y plays role of time, and such sections can be considered paths in solutions. Right? This formula 29 just represents something like paths in solutions to the spatial equation. And functions f and g can be chosen arbitrarily. So it's important to emphasize that all S sections are just given by pairs of functions. No real numbers now, because we consider S sections, not solutions. And the sections are encoded by pairs of smooth functions on the real plane and the base manifold, in this case. So we just need to define these functions. We need just to obtain some condition for these functions. And it's easy to see that G, if we are going to discuss solutions to the Laplace equation, then G must be y derivative of f, while f must satisfy the same Laplace equation, just written in terms of f. This is a description of solutions to the Laplace equation. This is the difference between S sections and solutions. The corresponding pullback reads as, yes, it's present here under the formula 30. And since we can choose functions f and g arbitrarily, then we can also perturb them in arbitrary way. And that is why the corresponding variational problem reduces just to the Euler-Lagrange equations for this action function, the corresponding action function. And it's easy to see that the corresponding Euler-Lagrange equations are given by the formula 31. Here we have the desired relation between g and f. G is y derivative of f, and besides we have the Laplace equation in terms of f. We can substitute this g here and obtain just the original Laplace equation. This means that all S stationary points are solutions to the Laplace equation, and vice versa, because all solutions are always S stationary points to any internal for any internal Lagrangian. So that is why we can say and vice versa here. And this is not a coincidence actually, because we have the following theorem. So if L is a horizontal in form and epsilon is the infinite prolongation of the corresponding Euler-Lagrange equations, let L be a horizontal in form and let epsilon be the infinite prolongation of the corresponding Euler-Lagrange equations. And suppose that S is the lift of a nowhere characteristic. Nowhere characteristic is important here actually. Suppose that S is the lift of an nowhere characteristic involutive hyperplane distribution on the base space. Then an S section sigma is an S stationary point of the corresponding internal Lagrangian if and only if sigma is a solution to the corresponding equation, to the equation by epsilon. So in the case of nowhere characteristic distributions, this theory works very well. And then one can ask the following question, like why gauge? Why do we need to consider something like gauge equations, gauge spatial equations, and so on? But the answer is pretty simple. It's because nowhere characteristic distributions is just not everything. We can have some more complicated situations, and let's consider such situations. So let's consider just the wave equation, the most simple equation, perhaps second order equation, the most simple equation in the world, if you want. Equation 32, but this equation is horrible in a sense. Geometrically, it's really horrible. I'll try to explain it right now. So suppose that let's consider the characteristic distribution given by the kernel of the covector field dy. Then any section has the form 33. Any section is given by an arbitrary function of x and u, taken as the right-hand side of this relation. Its x derivatives are defined unambiguously then, x derivatives of u. But y derivatives are not defined by this function f. And actually, the corresponding right-hand sides can be chosen arbitrarily. We only have to take functions of y only, of one coordinate. But these functions can be chosen arbitrarily. And here we have the infinite number of such functions. And this is quite a huge problem, actually, because here we have infinite number of almost arbitrary, half arbitrary functions, because they are functions of one variable only. And these functions are nothing but solutions to our spatial equation. They satisfy the infinite number of constraints given by the formula 34. And these constraints are almost the same thing as the spatial equation. Actually, the spatial equation also contains a relation like ux should be x derivative of the corresponding function on the right-hand side of this relation, and so on. But in essential sense, these constraints are our spatial equation. But in this case, we can solve these constraints, of course. It's easy to solve, but this is not the general case. We cannot solve them always, actually. And here we have the infinite number of constraints. Infinite number of constraints mean that if you want to apply something like Lagrange multipliers, then you have to find some idea how to do that, because the number of constraints is infinite. But this is due to specific of this example. It's a very horrible example, actually. Besides, perhaps it's one of the most horrible examples in this sense. And it's quite a weird situation because the equation is pretty simple, right? Yeah, and what about infinite number of the relations 35? If we want to describe solutions, then we should obtain these relations. H1 should be y derivative of f, right? If we deal with solution, then H1 is y derivative of f. And besides, Hi plus 1 is just y derivative of Hi. We should relate them if we discuss solutions. But the number of relations is infinite, right? Infinite number of relations. No internal Lagrangians can give an infinite number of relations. It's quite obvious thing. So here we have just no chance. That is, for any internal Lagrangian of the wave equation, the whole set of stationary points contains the whole set of solutions, but contains something else. They are not coincide. They not coincide. So apparently instantaneous states here are not just solutions to the spatial equation, but equivalence classes of solutions to the spatial equation. And that is why our stationary points are not just solutions. The whole set of stationary points contains something else. Apparently, it contains something that is equivalent to solutions in a sense. So let's define this sense. To define spatial gauge symmetries, we need to introduce some basic structures on our differential equation. We say that a pi epsilon vertical vector field on the total space is a symmetry of our equation if the corresponding Lie derivative of Cartan forms, the corresponding Lie derivative maps Cartan forms to Cartan forms. So nothing very special in this definition, just symmetry of our equation. Our equation is a manifold plus distribution, and the corresponding Lie derivative should preserve the ideal that corresponds to the distribution. That is, our vector field should preserve the distribution. A variational P form is an element of the vector space given by the formula 37. It's just Vinogradov's definition. Such vector spaces are elements of the Vinogradov's spectral sequence, are terms of the Vinogradov's spectral sequence. They belong to the first sheet of this spectral sequence, and they live in the corresponding cell, the corresponding cells. So they are variational P forms. Here we have some P times Cartan form, such that its the rank differential becomes P plus 1 times Cartan form. And we consider them modular elements of the sum, right? And this sum is just sum of P plus 1 Cartan form and the rank differential some Cartan form. And a presymplectic structure of epsilon is an element of the kernel of the differential that maps variational 2 forms to variational 3 forms. So it's just quite natural, pretty natural definition. We say that a presymplectic structure is a variationally closed 2 form. But here we have some additional structures, not just finite dimensional differential geometry. That is why we have to consider this additional structure Cartan distribution. We have to define variational forms as equivalence classes in order to consider this Cartan distribution. And instead of the Durand differential, we obtain variational differential. That is a differential that maps variational P forms to variational P plus 1 forms. And the presymplectic structure is an element of the corresponding kernel. So the same story as in finite dimensional differential geometry. An internal Lagrangian of epsilon generates a unique presymplectic structure If you can remember, internal Lagrangians arise as elements of some cohomology, and they arise with the corresponding spectral sequence. And it's important to say that presymmetric structures are also arise in this spectral sequence, and we have the corresponding differential. So internal Lagrangians generates presymplectic structures, and the corresponding differential is just induced by the de Rham differential. And this differential is also induced by usual de Rham differential. It's just de Rham differential on equivalence classes. So all symmetries of epsilon define morphisms of the form 39. We can consider interior products with the corresponding symmetries, with symmetries. And that is why we can define the kernel of variational two forms, say. And if we deal with the Lagrangian equation, then it's well known that we can define gauge symmetries of this Lagrangian equation internally in terms of the corresponding presymplectic structure, right? The Lagrangian generates a unique internal Lagrangian. This internal Lagrangian gives rise to the corresponding presymplectic structure, and we can consider the kernel of this presymplectic structure in the sense of the formula 39. And gauge symmetries are just symmetries that belong to this kernel. So if you have Lagrangian, then we obtain the corresponding internal Lagrangian. It gives us the corresponding presymplectic structure, and its kernel is formed by gauge symmetries. Let's discuss how we can define spatial gauge symmetries for gauge symmetries for spatial distributions, for spatial equations. First of all, we should define S symmetries, that is symmetries to spatial distributions, and they are defined in the same manner. Nothing special here again. And let me recall that we have already discussed that the fact that this inclusion gives us the dual inclusion. So modulus of the corresponding forms just contain modulus of Cartan forms. And such inclusions give us morphisms of the spectral sequences. And the morphisms are given by simple change of C to S. For example, a variational P form, it is equivalence class of this form, gives rise to a unique S variational P form, and the corresponding variational P form is given under the formula 42. So here we have nothing but change of C to S. We can do that according to this inclusion. And we call the corresponding elements as S variational P forms. So any variational P form gives rise to S variational P form. But S variational P forms are not just variational P forms for our spatial equation. We can consider our spatial equation in a separate manner. We can forget about Cartan distribution and consider only spatial equation. But S variational P forms are not variational P forms for our spatial equation in this case, because according to our spatial equation, S variational P forms have top total degree. They are forms of top total degree, because n minus 1 is top total degree according to our spatial equation. Our Cartan distribution believes that n minus 1 is not top horizontal degree, while our spatial equation believes that it's a top horizontal degree. That is why S variational P forms are not variational P forms for our spatial equation. So, and the main idea is that each Lagrangian produces a unique internal Lagrangian, which gives rise to the corresponding presymplectic structure, and the corresponding presymplectic structure leads to S presymplectic structure. That is how we can define S gauge symmetries or LS gauge symmetries, that is Lagrangian spatial gauge symmetries, but I'll call them LS gauge symmetries. So we can define LS gauge symmetries in the same manner, just as kernel of the corresponding S presymplectic structure. Elements of the kernel of the corresponding S presymplectic structure. Let's consider some examples. First of all, let's consider the Laplace equation again. We know that in the case of Laplace equation, we do not want to face something like LS gauge symmetries because everything is fine without them in this case, right? So let's consider the plus equation again. Let me recall that the corresponding spatial distribution is spanned by the total derivative with respect to x. And the parasymplectic structure is represented by the form dl, but it's easy to see that all multiplier in the first term and the first summand here is just annihilate the corresponding spatial distribution. So we can just cut this term off and consider the differential form omega, because this differential form omega represents the same as parasymplectic structure as dl. So we can deal with this differential form omega. Any S-symmetry has the form 46. Any S-symmetry is given by a pair of functions, phi and chi. These functions form something like characteristic of an S-symmetry, and they can be chosen arbitrarily. They are just arbitrary functions on our equation manifold. Then we should consider interior product of our S-symmetry, of an S-symmetry, and the corresponding form, and our form, differential form omega. The differential form represents the corresponding S-parasymplectic structure. And the result is written here. For the sake of simplicity, we denote uy by v, because now we are going to say that our spatial equation is nothing but the infinite prolongation of the following ODE system. This ODE system is highly underdetermined because this is ODE system for three variables, y, u, and v. But in essence, we have only one equation here. I just decided to add these relations for the sake of simplicity, just more convenient to consider like system of equations where the number of equations is equal to the number of dependent variables. But here we have three dependent variables, and in essence, we have just one equation for them. This is our spatial equation, right? It's easy to see that the infinite prolongation of this ODE system is nothing but our spatial equation. So we should calculate the corresponding S variational one forms. We are going to determine when the differential form 47 represents the trivial S variational one form. So we want to describe trivial S variational one forms. Any S variational one form is represented by a differential form 49. Here we have some arbitrary functions on our equation manifold, a, b, and c, and any S variational one form is represented by the differential form 49. We just need to understand how to choose a, b, and c. Oh, sorry? Is
No, it's
everything
okay.
fine? Oh, yeah, okay. We just need to determine when our coefficients a, b, and c lead to the trivial variational one form, to the differential form that represents the trivial variational one form. Well, in order to do this, it's convenient to consider linearization of a differential equation. If we have some differential equation, f equals to 0, then we can apply the corresponding evolutionary vector field to f, and we can change the roles of, we can just switch the roles of phi and f in this picture. We can say that the result is the same as the result of some of application of some operator on total derivatives to the characteristic phi. Then we obtain some linearization of our section f, and we can restrict this linearization to the equation manifold. That is how we obtain linearization of equation. And in the case of our spatial equation, the corresponding linearization is given by this square matrix, 3 by 3. It becomes square just because of these equations, because of these trivial equations. Without them, it's just the first row. But it changed nothing. So geometrically, of course, it gives us nothing, but it's convenient to consider everything in this way. And the corresponding adjoint linearization, formula adjoint operator, is given by this matrix, 3 by 3 again. And it's known that S variational one form is trivial if and only if the corresponding coefficients belong to the image of this joint linearization. This result follows directly from K-line theorem, the K-line theorem. So it's just nothing but corollary of the K-line theorem. The description of non-trivial S-variation one form. Non-trivial S-variation one forms are given by co-kernel of this adjoint linearization. So then trivial variational one forms are given by elements of the image of this adjoint linearization. So if we want to obtain trivial variation as variational one form, then we should put P and C equal to 0. Then the form 47 defines the trivial variation one form if and only if he and phi are equal to 0, because he and phi are just B and C in this picture. And this is why we have no non-trivial LS gauge symmetries in this case. And it's fine. Actually, it's fine because we don't want to fade them here. And there are no non-trivial LS gauge symmetries in this case. Okay, this is a good example, simple example. But what about the wave equation, our monster? So let's consider the wave equation again. Here we have just the wave equation, and the corresponding spatial distribution is given by, that is spanned by the total derivative with respect to x. Let's consider the following internal Lagrangian. It's easy to see that the first term is again just Lagrangian for our equation, and this is omega L, the corresponding form omega L. This form omega L is usually called something like presymplectic potential. Nothing special here. It's very well known construction actually. And theta 0 is nothing but restriction of this differential form to our equation, but in terms of coordinates in our equation, this restriction means nothing. We can say that we treat these variables as coordinates in our equation and so on. We just should not use derivatives, mixed derivatives as variables in our equation manifold, right? Because all mixed derivatives vanish in our equation. All other derivatives can be considered coordinates. And any vector field of the form 53 is an LS gauge symmetry for our equation, where phi0, phi1, etc. are arbitrary functions of the following arguments of y, uy, uyy, uyy, and so on. Okay. So if we consider them not just arbitrary functions, but arbitrary functions of this bunch of arguments, then we obtain LS gauge symmetry. Indeed, the form DL represents the same as presymplectic structure as the form omega. And if we consider the interior product of Wi-Fi and omega, then we obtain just the right-hand side, and it's easy to see that these forms and these forms represent the trivial variational one form, so the corresponding variational one form is trivial, and that is why all such symmetries are gauge symmetries, LS gauge symmetries, spatial gauge, not gauge, but spatial gauge symmetries. And let us note that if phi1 equal to total derivative with respect to y of phi0, etc., then y5 is the symmetry of the wave equation. So here we have quite special situation when decent symmetry of our equation, it was just real symmetry, not trivial symmetry of our equation, but it becomes spatial gauge symmetry here. So non-trivial symmetry of our equation becomes spatial gauge symmetry. Quite specific situation, but just because our wave equation is a monster in this sense. NS section sigma have this form here. Oh, again, it's just reminder because we have discussed this previously, right? Just function of x and y, arbitrary function of y.
Konstantin,
so
sorry.
Yes?
Just one question. Usually, of your usage of the term gauge symmetry, because usually we call gauge symmetry something which has unconstrained parameters, and in this sense, wave equation doesn't have gauge symmetry. And you call what's the difference between your definition and the standard one? Because these are conformal symmetries, which I suppose which you identify here. These are not gauge.
Yes, but they. I'll try to explain it a bit later. Actually, the difference is that we do not consider gauge symmetries in the usual sense. Spatial gauge symmetries do not allow one to consider compactly perturbed, compactly supported perturbations of solutions within the class of solutions. It's true. And this is the difference between usual gauge symmetries and spatial gauge symmetries. But spatial gauge symmetries also encode instantaneous states as equivalence classes. That is why they are gauge. So our solutions or S sections are not instantaneous states. They just represent the mathematical descriptions of instantaneous states, and their equivalence classes are the corresponding instantaneous states. I'm going to discuss it further. And that's why they are still gauge symmetries in this sense. I call them spatial gauge or LS gauge symmetries. And
but I suppose this should be related to. I suppose this should be related to something like gauge symmetries in Hamiltonian, because what you do is just Hamiltonian formalism. But
yes,
what do you call gauge symmetry in Hamiltonian formalism?
No, here I use just concept of LS gauge symmetry or spatial gauge symmetry. It's just different story. It's not just gauge symmetry.
I'm just trying to relate this to more like conventional terminology, because of course all this is kind of known in one or another.
I don't think that there is a conventional terminology still.
Well, case. For instance, what you call special equation is what are Hamiltonian constraints.
Yes, that's right.
Yeah, so there is a standard.
Hamiltonian constraints.
Oh, they are.
But this is intrinsic.
More or less by definition.
Yes. That's right. But they are intrinsic construction. They belong to intrinsic geometry, not to jets. And constraints belong to jets usually. So that is why there is no.
No, I mean constraint surface. Here. It's a gain equation. So if you take a gauge system, one way or another, it depends on methods. You get certain PDE, which is like in one dimension less, which is PDE of constraints, and this is your special thing. But some people prefer to think not in terms of time as a parameter. And for them, this PDE is still in one dimension. Okay, but anyway, you will explain perhaps this gauge symmetry.
Yes, it's not gauge. I would like to emphasize that it's spatial gauge symmetry. It's a gauge for spatial equation, but it's not usual gauge symmetry in the sense that such symmetries do not allow one to consider these compactly supported perturbations of solutions within the class of solutions. And this is the difference, actually. So any NS section has this form, and NS section sigma is NS stationary point of our internal Lagrangian if and only if the relation 57 holds. This relation is just the original wave equation in terms of f, but here we have no relations between f and h1, h1 and h2, etc. That is why we need these spatial gauge symmetries, or LS gauge symmetries, because any S stationary point can be transformed into a solution. Any S stationary point can be transformed into a solution of the wave equation using transformation phi1, where phi tau denotes the flow of this LS gauge symmetry. And this LS gauge symmetry is given by the following functions. Phi0 is trivial. Phi1 is just this combination of minus h1 plus dy of f. If you remember, we can consider, in order to consider LS gauge symmetries, we can take here anything, any functions of y, for example. And according to our equation, our restriction, the corresponding derivative dy of f is a function of y. So we can add it here, and it's still a gauge symmetry, LS gauge symmetry, not gauge. Yes, that's true. Not gauge symmetry, but LS gauge symmetry, spatial gauge in this sense. And we can consider such components, such functions, phi0, phi1, etc. And the corresponding transformation phi1 relates any stationary point to a solution of our spatial of our wave equation. Solutions to the spatial equation have the form 59, if you remember, right? Just some function of x, and uy is just some constant, because solutions are given by functions of x only and constant. They should not depend on y, because we fixed y. We have already fixed y, actually, since we discussed solutions. So they are just functions of x or functions of nothing if they cannot depend on x, like how it works in this case. So we have just constants C1, C2, but our LS gauge symmetry allows one to gauge them away, to gauge these constants away. So our initial data, in the sense of initial state, initial data in some gauge sense, is just function a of x modulo some additive constant, C1 modulo another additive constant, just arbitrary additive constant, and so on. We can kill this C1, C2, etc. And our initial state is just encoded by function a of x, consider it modulo some additive constant, arbitrary additive constant. And the corresponding solution to this spatial gauge Cauchy problem, so the Cauchy problem in this gauge sense, spatial gauge sense, the solution is unique. The corresponding solution is unique, so we can consider Cauchy problems on characteristics using this spatial gauge construction, LS gauge symmetries, using this LS gauge symmetries. Because the corresponding solution in this sense is unique, and this means that it's reasonable to say, in a sense, reasonable to say that our states are encoded not by just solutions to our spatial equation, but by the corresponding LS gauge equivalence classes of solutions. Actually, we have no definition of LS gauge class still, and I'm going to give it a bit later. But it's easy to see that it makes some sense, at least it makes some sense to say that our instantaneous states are given by not just solutions to our spatial equation, but by equivalence classes, LS gauge equivalence classes of solutions. And that's why I decided to use this word gauge in this sense, because again, we obtain description of some, say, phenomena, not in terms of solutions to the corresponding equation, but in terms of equivalence classes to the corresponding equation. And this gauge symmetry just changed the description of the phenomenon. Phenomenon remains the same, but our gauge symmetry just changed the description, the mathematical description of this phenomenon. I think that this idea justifies the word gauge in this context, but maybe I'm not right, I don't know. So this is my explanation for this word. So let's go further. We need to define LS gauge equivalence now. If we have if LS gauge symmetry generates a global flow on our equation manifold, then the corresponding transformations play the role of spatial gauge ones in the sense of the previous slide. And for a given spatial equation S, the set of all such transformations generates a group, which we call LS gauge group. Group operation is just composition. So the whole set of such transformations that we obtain using the flows of LS gauge symmetries, the whole set of such transformations generates the corresponding LS gauge group. And this gives us some equivalence relation, right? So we can say that two S sections are LS gauge equivalent if they are related by some LS gauge group transformation. So some transformation that belongs to a LS gauge group, the corresponding LS gauge group. So if an equation epsilon is embedded into a certain infinite jets, and L is a horizontal n form such that its variational derivative vanishes on epsilon, then L gives rise to a unique S variational one form, actually. Not cohomology class of L, horizontal cohomology class, but L itself. L itself, at least L itself, gives rise to a unique S variational one form. And this is how it should be in classical mechanics, because in classical mechanics, Lagrangians or Lagrangians and Hamiltonian form are just one forms, and of course they are variational one forms at the same time. But they are, first of all, they are one forms, and we would like to have something like S variational one form here as a candidate for action. And it's true because if we have an S variation of one form and we have some additional condition satisfied, then the action 60 is well defined on a section provided the term is compact and oriented. And the condition is that for each point of our boundary, perhaps M has a trivial boundary, and then for each point of this boundary, the plane of our distribution on the base space coincides with the tangent plane to the boundary. If this condition is satisfied, then the action 60 is the action that is given by our S variation one form, is well defined on S sections, provided the term is compactly oriented, of course, because we would like to not to face some problems with the definition, some technical problems. That is why we require that M is compactly oriented. Let's consider the following example, the example of Maxwell's equation. Let epsilon be the infinite prolongation of the Maxwell equations 61. Here, M, our base space, is just real n-dimensional vector space. F mu denotes the difference between d mu a nu and d nu a mu. A nu are components of potential or components of connection one form, if you want, to connection one form. We use the metric, the diagonal metric, with +1, -1, etc., -1 on this diagonal. Let's introduce local coordinates on, not local, but coordinates on our base space, x0, x1, etc., xn -1. And mu and nu are indices. They can take all the values, 0, etc., and -1. And we also assume that n is greater than 2. We are going to use the spatial indices, I, j, k. They can take all the spatial values 1, etc., and -1. And it's well known that the Maxwell equations are just Lagrangian equations for this Lagrangian given by the formula 62. We can construct the corresponding form L plus omega L, and we would like to restrict this form to the equation manifold in order to obtain a representative of the corresponding internal Lagrangian. So we can do that, of course, and let's consider the most natural choice for the spatial equation. Let's consider the kernel of the vector field dt on our base space and its lift. Then the S per symplectic structure is given by the form 33. It's easy to see that we should not have dt here, actually. If we want to consider the corresponding S per symplectic structure, we are going to take the drum differential of the restriction of this form. And we know that the drum differential of the restriction of this form is just twice Cartan form. But if a term here have something like multiplier dt, then the corresponding term in the S per symplectic structure is trivial. So we just need not consider here some terms that contain dt. That is why we should not allow mu to be non-trivial, non-zero in this form. If mu is non-zero, then dt arrives here, and the corresponding term is trivial. So we only need d0 here. Only need to consider d0 here. The corresponding S per symplectic structure has this form, the form 63, and here theta 0I is just the notation for such differential forms. And theta I is just theta I bar is just the restriction of the basis of these basis forms to epsilon. Yes, we should introduce some local coordinates. In order to simplify everything, we should introduce some coordinates, not local actually, global coordinates on our equation manifold. Of course, we can consider x mu as coordinates on epsilon. And besides, we should add something else. We can consider a new f0I as coordinates on our equation, as independent coordinates, and the corresponding derivatives, d0 is 0, d0 twice is 0, and so on. And besides, we should consider also spatial derivatives of these coordinates as coordinates on our equation manifold. except for, say, d1f01 and its spatial derivatives. We should just choose somebody and say that such functions are not coordinates on our equation manifold. So let's choose this function and its spatial derivatives and say that they are not coordinates on our equation manifold, while all other spatial derivatives of these guys are coordinates on our equation manifold. We can do that, actually. And the fact that we can consider coordinates in this way is just the very role of Legendre transformation, the only role of the Legendre transformation. Yeah, let me note that here we have infinitely many degrees of spatial freedom of this form. They are degrees of spatial freedom because according to spatial equation, they should be considered independent. They should be considered new dependent variables according to our spatial equation. That is why they are degrees of spatial freedom. For the Maxwell equation, they are not degrees of freedom, not separate degrees of freedom, but for spatial equation, they are. So NES symmetry has the following form, the form 3064. Here we have some arbitrary functions, phi, phi0, phi1, etc. They can be chosen arbitrarily, and the functions eta I must satisfy one additional equation. This is just the consequence of consequences. Yeah, this follows. This requirement follows from our spatial equation. dy are restrictions of spatial total derivatives to the equation manifold because index I goes 1, etc., and minus 1. It cannot take zero value. So let's consider the corresponding interior product. It gives us the following differential form, and we would like to understand if this differential form represents the trivialist variation of one form. So this differential form represents the trivialist variation of one form if and only if eta I equal to zero, all of them. And there exists a function such that I are just the corresponding total derivatives of this function. So we obtain the corresponding description of LS gauge symmetries. LS gauge symmetries are just S symmetries, where we have eta I equal to 0, and I are just the corresponding total derivatives of the same function epsilon. Yes, it's more convenient to consider LS gauge symmetries in this way. We can just consider only LS gauge symmetries only. Yes, they are given by arbitrary functions epsilon phi0, phi1, and they have this form. And the degrees of spatial freedom, it's easy to see that our degrees of spatial freedom are spatial gauge ones, right? Because we have arbitrary functions here, phi0, phi1, etc. Arbitrary functions. We can use arbitrary functions here in order to obtain the corresponding LS gauge symmetries. So this is why we can just gauge these degrees of freedom away. So they are spatial gauge, but they are not gauge in the most literal sense. Because the gauge symmetries of the Maxwell equations, they have this form. They are given by such functions. Phi0 should be time derivative of this function epsilon. Phi1 should be time derivative of phi0, etc. And in the sense of just gauge symmetries of Maxwell equations, we cannot get rid of these degrees of freedom. So the whole huge gauge group of Maxwell equations is just too small to gauge them away. And this LS gauge group is way bigger than the gauge group and is just big enough, just great enough, huge enough to gauge them away. So NES section sigma has the following form. NES section is given by some functions phi nu, gi, h1, h2, etc. And vice versa. Which functions also determine a unique S section in this way. Yes, function f nu, h1, etc. can be chosen arbitrarily, while our functions ji must satisfy the Gauss law, one constraint. This constraint is nothing but Gauss law. This is our condition we should satisfy this condition. Otherwise, we obtain something but not a section. If we are going to deal with a section, then we should consider such functions ji, functions that satisfy to this requirement, this restriction. Yes, and of course, this is nothing but constraint, maximum what you just mentioned, and this constraint arises here in natural way. We just deal with our spatial equation and obtain this constraint is the requirement in order to deal with S sections in this case. Yeah, here d mu f nu, d mu gy, and so on denote the corresponding partial derivatives, while the notation di a nu and so on is indivisible. They are not derivatives of a nu in the literal sense. They are just indivisible notation. So they're just coordinates on our equation manifold. So d mu f nu are real, literally they are partial derivatives, while this is not literally partial derivatives. They are coordinates. So any LS gauge symmetry has this form, any section has this form, the corresponding form, and any LS gauge equivalence class of S sections has the form 1771, right? We can consider, if we deal with S sections, then we cannot consider something like derivatives of, say, a di of a nu and so on, because we already deal with sections. They should be functions of coordinates on our base manifold already. That is why we have to deal, if we deal with sections, then we deal with functions of coordinates on the base manifold only. So an LS gauge equivalence class of S sections has the following form, right? It's given by just functions fi modulo the corresponding derivatives of some arbitrary function. Besides, we have functions ji. They encode our equivalence classes, because the corresponding functions f0 and h1, etc., can be chosen arbitrarily because they should be considered modulo anything, since we can consider anything here. So they should be considered modulo anything. That is why they are not essential in this case, and any LS gauge equivalence class is given by such functions. And it's, yeah, here epsilon is a function on the base manifold already, not function on our equation manifold, because we consider sections of our equation. And if n is equal to 4, then LS gauge equivalence classes of solutions to the spatial equation are in one-to-one correspondence with tuples of this form: time moment, the corresponding instantaneous electric field, and the corresponding instantaneous magnetic field, because these functions ji are nothing but components of instantaneous electric field, maybe up to sign, maybe they should be considered as minus, but it's not that important here. So ji encode electric fields, and the corresponding equivalence classes, fi modulo such additive functions, they precisely encode magnetic fields. So it's easy to see now that LS gauge equivalence classes of S sections are nothing but paths through instantaneous states, instantaneous pairs of or tuples of electric field and magnetic field. So their physical meaning is quite good in this sense. It shows that everything works properly. Oh, let's consider the corresponding variational problem. We should consider the pullback and the corresponding action, but we also have one constraint here. We have constraint variational problem. And we can try to apply something like Lagrange multipliers method, but to be honest, I don't know if we can do it all the time, or maybe we cannot do it in some problems. That is why I'm not going to use it here. I'm going to just to obtain honest solution to this problem. So I'm going to resolve this constraint in this form. This constraint is nothing but some closeness of some differential form, and it can be resolved in this form using the exact differential forms. Not differential forms actually, but families of differential forms, because we also have time here. We have coordinate t here, and of course these derivatives are just spatial derivatives. They involve no time derivative. Nevertheless, we can resolve this constraint and substitute everything for our action. We obtain this variational problem. And the very fact that we resolved constraint in this way, in this local manner, is important, actually, because for any compact-oriented n-dimensional submanifold of our vector space, we can take as variations delta, phi nu, etc., arbitrary functions of our vector space that vanish with all their derivatives on the boundary, and such that delta rij equals to minus delta rji, of course. This fact, the fact that we can choose them arbitrarily, follows from the locality of the corresponding solution to our constraint. So this locality is extremely convenient here. That is why we can avoid the whole Lagrange multiplier method story and so on. And then the variational problem reduces to the corresponding Lagrange equations, equations 74. And the latter equation here is just nothing but condition of existence of some function. So this function, actually this function plays a role of Lagrange multiplier. If we try to use Lagrange multipliers, then this function is Lagrange multiplier. But we are not going to discuss Lagrange multipliers here. We use another approach. So the latter equation is just equivalent to the existence of such function, such that the equation 75 satisfied. And we can rewrite the corresponding equations that determine S stationary points in the following manner. It's just two equations. These equations involve lambda, of course, but it's not a problem. We're going to discuss it a bit further. And it's easy to see that these equations are nothing but Maxwell equations in Hamiltonian form, standard Maxwell equations in Hamiltonian form, except for Gauss law, dij equals to 0. But the Gauss law is satisfied by any stationary point, and of course, by any S section. Of course, any stationary point being a section also satisfies this law. So our system of equations for S stationary points is nothing but Maxwell equations, except for this lambda, right? But we can kill this lambda, of course, using less gauge symmetries. Any stationary point has this form, and it can be transformed into a solution using phi1, where phi tau is the flow of this less gauge symmetry, where we put phi0 equals to minus lambda, phi1 equals to this guy. It's not important to consider phi1, etc., actually, because nothing related to phi1 and phi2 right here, and we know that we can choose them arbitrarily. They are just arbitrary components of less gauge symmetry. We can choose them arbitrarily, right? So we have to care about phi0 only, because something related to phi0 arises here in this bad manner. I mean, f0 minus lambda, some alien lambda appears here. So, but we can consider the corresponding less gauge symmetry, and this less gauge symmetry just says that instead of v nu, we can consider the corresponding S section such that A0 equals to F0 minus lambda. It becomes just component of our S section, and then the corresponding S section satisfies to the Maxwell equation. This means that any stationary point can be transformed into a solution of the Maxwell equation using such flow, using the flow of the corresponding less gauge symmetry. And it's a good news, actually. Right? At least I think so. So we can make the following remarkable conclusion. All the stationary points of the Maxwell system are less gauge equivalent to its solutions. Let me recall again that everything happens intrinsically here. We have no jets, actually. Jets play the following role. We use Lagrangians on jets, right? But we rewrite them intrinsically. So everything is written in terms of the intrinsic geometry now. We need not consider some embeddings to jets and so on. That is why the whole story about ambiguous prolongation of internal Lagrangians to jets is not important. So, and since Maxwell equations are not Lorentz invariant, the same conclusion can be made, of course, for all spatial distributions that one can obtain from this S, from our S, using Lorentz transformations. This is what concerns Maxwell's equations. Now let us consider another example, an example of a variational equation that is not a Lagrangian one. The potential KdV equation is not a Lagrange equation for some variational problem, but it admits some differential consequence such that this differential consequence is just the Euler Lagrange equation for some Lagrangian. That is why this equation is still variational. The corresponding internal Lagrangian is non-trivial. This is why I call this equation variational, because this equation possesses an non-trivial internal Lagrangian. But this is not a Lagrangian equation itself. And the corresponding Lagrangian that produces a differential consequence is given by the formula 80. We can choose t, x, u, ux, etc. as local coordinates, not local, but coordinates on our infinite prolongation of the potential KdV equation. And of course, the Cartan distribution is spanned by the corresponding total derivatives. The corresponding internal Lagrangian is represented by the differential form 82. Here, theta 0, theta x are nothing but restrictions of the corresponding basis contact forms to the equation manifold. And let S be the lift of the distribution, the kernel of the corrector field dt. It's also characteristic distribution, right? The only one characteristic distribution here. So the S perisymplectic structure is represented by the differential form omega, and the NS symmetry of the potential KdV equation has the following form, the form 84, right? NS symmetry is given by one arbitrary function. This function can be chosen arbitrarily, yes. And then we should consider interior product. The interior product has this form, and it's easy to see that on the right-hand side, last two terms represent trivial S perisymplectic S variational one form, so everything depends on this term only. And our LS gauge symmetries are just given by the kernel of this operator, that is by functions of t, of one variable t. So here we have non-trivial LS gauge symmetries. And as stationary points here are actually LS gauge equivalent to solutions. Let's consider this. Let me explain this. And S section has this form, is given by one function of x and t, arbitrary function of x and t. The corresponding pullback has this form, the form 86. And as stationary points are described by the corresponding Lagrange equation again, because we can choose f arbitrarily, we can perturb it arbitrarily. That is why everything reduces to the Lagrange equation. And the corresponding Lagrange equation has this form because it's just a single equation. And this equation is just nothing but the requirement that there is some function of time such that this equation holds. If we denote by phi tau g the flow of such LS gauge symmetry, then the transformation phi 1g relate the corresponding S stationary points that correspond to this function g, the same function g here. This transformation relates S stationary points to solutions of the potential KdV. So here again we have the same situation, quite weird situation actually in this case, but still again we have the same situation when all the stationary points are LS gauge equivalent to solutions. But it's not that usual thing actually for this example. Let me explain it. So it's well known that the potential KdV is related to the KdV itself, the KdV equation. It's just nothing but an introduction of potential. So here we have the corresponding differential covering between potential KdV and KdV itself. And in local coordinates, local, they're just global coordinates in this case. In coordinates, the differential covering is given by the formula 88. V equals to ux, vx equals to uxx, etc. So we have this remarkable differential covering. And it turns out that this differential covering rho establishes the one-to-one correspondence between LS gauge equivalence classes of S sections of the potential KdV and the corresponding sections of corresponding spatial equation of the KdV equation, right? So here we have the spatial equation that is spanned by total derivatives with respect to x, and this spatial equation produces a spatial equation for KdV, and the corresponding spatial equation is also given by total derivative of x, but this total derivative lives on the infinite prolongation of KdV. So here we have two spatial equations, and they are related. The same differential covering relates spatial equations as well. And less gauge equivalence class of S sections are in one-to-one correspondence to S sections of the corresponding sections of the KdV. Moreover, ρ establishes the one-to-one correspondence between the less gauge equivalence classes. Oh no, not the less gauge equivalence classes. Yes, it's true. Less gauge equivalence classes of S stationary points and solutions to the KdV. So our less gauge equivalence class of S sections are nothing but sections of KdV, the corresponding sections of KdV. And our stationary points are solutions to the KdV. Thus, in this example, less gauge symmetries lead to the description of dynamics given by another equation, because spatial gauge Cauchy problems here for the potential of KdV are nothing but Cauchy problems for the KdV. And if we consider the dynamics given by the internal Lagrangian, then this is just KdV. So using this potential KdV, we obtain KdV itself. This is why this example is a bit weird, but of course, the original pre-symplectic structure was degenerate in the most literal sense. So it's not surprising eventually. But this is the reason why one can say that it's not a good idea to consider less gauge symmetries in all this story for non-Lagrangian equations. Yes, of course, this equation is variational in our sense, but it's not a Lagrangian equation. And maybe this is the reason why we should not consider less gauge symmetries and all of this, and just consider it's just the corresponding spatial equation is non-gauge equation and so on. So it depends on point of view. Yes, and let's discuss the covariant variational principle that arises here. So suppose that L is an internal Lagrangian of epsilon represented by differential form L, and a section sigma to the same bundle, to our equation bundle, is an almost solution if for each x, if for each point of our base, the inequality 89 holds. Here we have nothing but dimension of the intersection, this intersection. We take some point of our base, and we ask sigma to send the corresponding tangent plane to epsilon, and we obtain just tangent plane to epsilon and the corresponding point sigma of x, and we consider intersection of this tangent plane with the corresponding respective pattern plane, and require that the dimension of this intersection must be at least n-1. Actually, if we have here n, if the dimension is always n, then our sigma is nothing but solution to our equation. That is why I use this terminology, almost solution, because if it's equal to n, then we deal with solution, and if it's just n-1, then we deal with almost solution. Of course, solutions belong to the whole set of almost solutions, right? They're just members of the set. And let's define pairs in almost solutions, define them the same way, nothing special. The mapping is a pair in almost solutions, and the corresponding mapping of tau are almost solutions of epsilon for all tau. The important thing here is the almost gauge equivalence relation. So we say that almost solutions sigma and sigma prime are almost gauge equivalent, and there exist diffeomorphisms phi1, etc., phi k, such that the following four properties hold. First of all, each fi is an Si gauge transformation, where Si is a spatial distribution on epsilon. Here I use not LSI gauge transformation, but Si gauge transformation, because one can say that maybe there are some other reasonable concepts of spatial gauge transformation, spatial gauge symmetries, and so on, and we must not consider less gauge symmetries in some cases, not all the time at least, and maybe one should consider some other groups of spatial gauge transformations It doesn't matter actually. We can choose any group of special gauge transformation, everything works here. So it's just scheme. It's not variational principle itself, it's just something like scheme for variational principle. So each Fi is SI gauge transformation. Sigma should be an S1 section. Each composition of this form should be I plus 1 section, or I from 1 to k minus 1. And sigma prime should have this form. This looks a bit cumbersome and maybe a bit weird, but let's discuss some physical interpretation. Maybe this interpretation is a bit stupid, but still it clarifies something. So, loosely speaking, our spatial distributions are just observers. Let's suppose that we have a bunch of observers, observer number 1, etc., observer number k. And sigma is an S1 section. That is, sigma describes something like time evolution for the first observer. But according to the first observer, this composition, since F1 is a gauge symmetry, as S1 gauge symmetry, this composition describes the same phenomena. But it may happen that this composition also describes something like time evolution according to observer number 2, or observer number 2. Then, from his point of view, this composition describes the same phenomena. Since observer number 1 and observer number 2 live in the same universe, we have to consider them at the same time. That is why we have to consider such compositions as well. And then, according to observer number 2, this composition describes the same phenomena, and so on. This is a bit simple but maybe stupid explanation of this almost gauge equivalence. Like just physical interpretation. I'm not sure that the idea to interpret it physically is a good idea, actually, but at least it makes the whole definition not that cumbersome in a sense. More understandable, it makes it more understandable. And an almost solution sigma is a stationary point, not S station, but just stationary point of our internal Lagrangian. If for any compact oriented n-dimensional submanifold, the relation 91, the same relation holds for each path and almost solutions. Actually, we can consider not just S sections, but all almost solutions, and we can perturb all the solutions within the class of all almost solutions, and everything will be excellent still. Everything works still. So, our covariant canonical principle is as follows. An almost gauge equivalence class satisfies the covariant canonical variational principle if it can be represented by a stationary point of the internal Lagrangian L. Yeah, let me emphasize that the choice of a representative of L has no impact here. Nothing depends on the choice of a representative. Solutions of a variational equation produce almost gauge equivalence classes that satisfy the covariant canonical variational principle. That is what we would expect, right? In this sense. And again, we have no concept, no role of time, no time involved here. Of course, we use the word time, but time was just some coordinate on our base manifolds. It was just for coordinate description. It was convenient for coordinate description, but the whole construction involves no time here. And it's a bit weird, maybe. So it means that the whole thing about variational principles, Hamiltonian or just covariant, in this sense, doesn't based on time. It's not based on time concept. And my final idea that if we have our equation and this equation is embedded to some jets manifold, and we have a Lagrangian such that its variational derivative vanishes on epsilon, then this Lagrangian gives rise to a unique element of this group. Actually, we've mentioned this group in the very beginning of my talk. And each Lagrangian produces a unique element of this group. Then if M is compact and oriented, then the action 93 is well defined on all almost solutions such that for each point of the boundary, the inclusion 94 holds. So our point at each point of the boundary, the corresponding tangent plane to the boundary should correspond to something that belongs to the Cartan plane. Differential of our section sigma, almost solution sigma, should send this tangent plane, tangent to the boundary, the plane tangent to the boundary, to something like subspace of Cartan plane, the corresponding Cartan plane. This action is well defined in this case. Yes, I should mention main weakness of this approach. Of course, constraint variational problems may arise due to the non-triviality of spatial equations, right? We can face non-trivial spatial equations, and actually this is our main idea, to face non-trivial spatial equations and to deal with them somehow. But constraint variational problems may arise here. And fairly speaking, I don't know if one can use the whole Lagrange multiplier story, Lagrange multiplier method, to deal with such constraint variational problems. It's clear that if we use this Lagrange multipliers method, that everything we obtain is just as stationary points, or say stationary points and so on. All solutions to the corresponding equations, all Lagrange equations, are as stationary points, but it's not clear if the Lagrangian multiplier approach can give us all stationary points. Maybe some of the stationary points cannot be obtained using this approach, I just don't know. And this is the main weakness of this construction. Oh yeah, let me mention some literature. These three papers contain a more detailed version of this talk. These two papers, due to Maxim Grigoriev, contain another approach in terms of intrinsic Lagrangians. This is another approach to encode variational principles in terms of the intrinsic geometry. And this book contains just basic information about the geometry of differential equations. The paper by Vinogradov contains the definition of C-spectral sequence and no description. And this paper by Alexander Moiseyevich Verbovetsky contain the corollary from the K-line theorem that is important for the discussion of this topic. It was important for this topic. So, thank you. That's all. That's it.
Thank you. Questions, remarks? Maxim, don't you want to comment? Was to stop? No.
Yeah, I'm here, but maybe,
yeah,
maybe someone has questions before. Well, I'm not sure I have something concrete to say.
Nevertheless. Okay. Kostya,
I can.
yeah.
No, I only wanted maybe to comment a bit about Hamiltonian formalism, because I think what Konstantin does is kind of Vinogradov type, let's say, approach to what physicists, at least physicists, what they call Hamiltonian formalism. And
yes,
perhaps this part can be made more explicit, and it will be useful because people, of course, consider similar things. So I think it's interesting what Konstantin explained, because it gives quite precise. So that's the only comment I can make. But it's to make it more explicit. It's probably one needs more time to explain. Maybe next talk, Konstantin will do better explanation of the relation to Hamiltonian formalism.
Yeah, thank you. Yeah. May I have a comment here? Yeah, I just must emphasize that this description is just description in terms of the intrinsic geometry. We involve no jets at all. Jets play only role, the only role of jets is to give us variational, to give us action, starting point. Our starting point is action on jets, but then we just need not jets. And we can consider internal Lagrangians, of course, without any story about jets. We can consider it intrinsically. So basically, this is the very Hamiltonian formalism. It's true, but written in terms of the intrinsic geometry. It's nothing but Hamiltonian formalism rewritten in terms of the intrinsic geometry. And this is the only difference, because as far as I know, physicists usually consider jets and consider everything on jets. That is why they do not face such special gauge symmetries and so on. Oh, yeah, sorry.
Kost, you don't need jets, but you essentially need the bundle structure of the equation, yes?
No, actually it's not true. Actually, it's not true. We can just explain everything without bundle structure. It's just for simplicity. For the sake of simplicity, I decided to use this bundle structure, but it's not required at all. Eventually, we can define everything without bundle structure.
Okay.
It was just simplification.
See how it works. Okay, thank you. More questions, more remarks? Okay, thanks a lot for visiting and attending the seminar. Question again, thanks a lot for a very interesting talk. Well,
Thank you. Yeah.
bye, and see you later. Hopefully. Bye.
Thank you. Bye.
Bye.
Good night. Yeah.